Okay guys, we're going to start our next unit here, solving by systems by graphing. And so we know now that there are three possible scenarios with systems. Systems are two equations at the same time, or at least two equations at the same time. We're only working with two in Math 8. There are three possible scenarios. Our lines could intersect once, and we know that that gives us one solution. And the actual solution, if I ask what is the solution, is the ordered pair where the two lines intersect. I could have two parallel lines which never intersect, therefore have no solution. And the last possible scenario is when I have the same equation that comes out to be the same line on top of itself, which provides infinite solutions, because the lines are going to intersect at every point ever, infinitely. So we can actually find these out just by looking at the equations, not necessarily the exact point of intersection, but we can tell just from our equations if they're going to be one solution, no solution, or infinite solutions. We've talked about if they're in slope-intercept form. So if they're both in y equals mx plus b, they're both in slope-intercept form. Just by looking at the slopes and the y-intercepts, I can tell which scenario it's going to come out to be. If my slopes are different, so if slopes are different, no matter what the two slopes are, no matter what the two y-intercepts are, if slopes are different every single time, these two lines are going to intersect somewhere. Might be way up, might be way off the graph. But if my slopes are different, there's going to be one solution. Now you might have to graph them, substitute, or eliminate to find out what that point is, but you know they're going to intersect somewhere. If our slopes are the same, but the y-intercepts are different, we know that they're moving at the same rate, but they're not starting from the same place. They're going to be parallel every single time, which means it's no solutions. The last scenario is if the slopes and the y-intercept are the same, then it's going to be the same equation. If everything's the same, it's the same equation, which means it's the same line, which means it's going to have infinite solutions. So there are many times, especially if I just ask how many solutions, that you don't even have to graph, substitute, or eliminate. You just have to be able to tell me, is it going to intersect, not at all, or forever? So one, none, or infinite. But if I actually ask what the solution is, I have to know what is the point of intersection, and if they don't intersect, you type no solutions. If they are the same line, you type infinite solutions. Okay, so let's recall how to actually solve by graphing. So in order to graph, both equations need to be slope-intercept form. This time both of them are. I always start with my y-intercept. I know that that's the number without an x next to it. It's the constant. So that tells me where to put my beginning point on the y-axis. So I go down to -8, so 1, 2, 3, 4, 5, 6, 7, 8, and I put a dot. If my slope just looks like an x, I got to remember that's an understood 1. This time it's a positive 1. So every whole number has an understood 1 underneath it. So my slope for this equation on top is really a positive 1 over positive 1. So I got two options. I can go up 1 and right 1, or I can go down 1 and back 1, because that's like a -1 over a -1, which still comes out to be positive 1. So starting from the y-intercept, not the origin, starting from the y-intercept, I'm going to go up 1, right 1, and I'm going to make as many points as possible, repeating this pattern of up 1, right 1, so that I can make really accurate lines. If I have some other dots to make, I can go backwards, going down 1, back 1. So there is our first line, that y equals x minus 8 line. Then if we try to graph the next equation, I'm going to start at a positive 1, because that's my y-intercept. My slope is -2, that's a -2 understood positive 1 on the bottom. So negative 2 over 1 means I need to either go down 2 and right 1, or I could technically go up 2 and back left 1. So either one of those movements. So if I'm going if I'm going down 2 and right 1, I'm going to repeat that pattern. Down 2, right 1, down 2, right 1, down 2, right 1. Keep repeating it as far as I can go. If I want more the other way, I could go up 2 and back 1. Just make it really accurate here. So here's my other line. Okay. So I'm looking for the point where they intersect. Where they overlap, the reason I'm being really exact is because I want to know the actual point. Now when I'm reading an ordered pair, I do start at the origin. This goes over 3 positive on x and then down 1, 2, 3, 4, 5 on y. So it's x comma y, that's how an ordered pair is. So it's positive 3, negative 5. So 3, negative 5. That is the point of intersection. That's the solution to our system. So we'll try one more. This one, well, one more, that's in slope-intercept form. So this one's still in slope-intercept form, still starting at the y-intercept. Don't have to rearrange. I'm going to start at 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Put a dot. My slope's a positive 1/2. So 1/2 positive means I can go up 1 and right 2, or I can go down 1 and back 2. So if I go up 1 and right 2, I'm out of graph. I need to do that reverse option. Down 1 and back 2, down 1 and back 2. Just keep doing it as many times as I can. There's my first line. Next equation, I'm going to start at a positive 6. So 1, 2, 3, 4, 5, 6. Put a dot. It's my y-intercept. There's nothing but a negative in front of the x, so I know that's an understood negative 1. If my slope's negative 1, I know there's an understood positive 1 under there, because every whole number has a positive 1 underneath it. So I can go down 1 and right 1, or I can go up 1 and back left 1. So if I go down 1, right 1, and I'm making my dots this way, I'm not going to see where it's intersecting. I need to go the opposite way. So I need to go up and back, up and back, up and back, up and back. So now I see where they're intersecting. Got to identify that ordered pair. Again, I read that ordered pair from the origin. It goes back 2 on x, so that's negative 2. Then it goes up 1, 2, 3, 4, 5, 6, 7, 8 on y. So negative 2, 8 is the ordered pair where these two lines intersect. So now we'll try one where we actually have to solve for y. Neither one of these equations are in slope-intercept form, so I have to get y alone. I need to move the x term first. Since it is minus 3x, I am going to do the opposite and add 3x to both sides of my equation to get it to cancel on the left. And I have y equals 8 plus 3x. Since nothing is left in front of y, I'm technically done, but we usually see it written as y equals mx plus b. Well, if you can recognize that 3 is the slope and 8 is the y-intercept, you don't have to rearrange it, but if it makes you feel better, you can switch the places to put it in the right format. Just remember that the sign in front of the number stays with that number. This time it's not a big deal because both the 8 and the 3 are positive, so when I rearrange it, it's still going to be y equals 3x plus 8. If I solve the second equation, I need to move the x first. It's a minus 1x, so I'm going to add 1x to both sides. There's nothing in front of y, so I've got y equals negative 2 plus x. Again, if I want to rearrange it to put it in y equals mx plus b form, I got to remember that the 2 was the negative and the x was the positive, so y equals a positive x minus 2 is the second equation we'd be graphing. So now we have both equations in slope-intercept form. We're going to do what we always do when we're graphing from slope-intercept form. I will start with the y-intercept, which is 8. 1, 2, 3, 4, 5, 6, 7, 8. Put a dot. My slope is a positive 3. That's over an understood 1. So I can go up 3 and right 1, but I ran out of room, so I need to do the reverse. Down 3, back to the left 1. Down 3, back to the left 1. Okay, so down 3, back to left 1. I'm just going to do it as many times as my graph will allow me so I can get the most accurate line possible here. Okay, so there is my first line. The second one, I have to start at a -2 because that's my y-intercept. There's just an x. I know it's an understood 1 over an understood 1. So 1 over 1, so I can go up 1, right 1. And I could keep making dots this way, but I see the intersection is going to be back this way. So I need to go down 1 and back 1. Okay. So I've got my other line, and I'm looking for the point of intersection. So this ordered pair, starting from the origin, it goes back 1, 2, 3, 4, 5. So on x, it's -5. Then it goes down 1, 2, 3, 4, 5, 6, 7 on y, so -7. So your solution to this one is the point -5, -7, but we had to properly solve for y first. All right, number 4, one of them is already in slope-intercept form, but the top one's not, so we need to do something about that. We need to get this y alone in the top equation. So in order to do that, I'm still going to do the same thing of trying to get x to the other side first, because x and y are on the same side. This x is understood to be a positive 1x, so I'm going to minus 1x from both sides. And I'm left with 2y equals 4 minus x. Now, previously we were done because there was just a y. This time there's a 2 in front of y, so I need to divide everything by it because it's being multiplied by y. Divide everything by 2. So 4 divided by 2 gives us 2, and there's an understood -1 right here in front of x. So -1 divided by 2 will give me a decimal, so I'm going to leave it -1/2 x. So if I rearrange it, I don't have to, but if I choose to rearrange it, y is equal to a -1/2 x and a +2. So there's our first equation rearranged. The second one was already in slope-intercept form. A lot of you will notice before I even graph that both the slopes are the same and the y-intercepts are the same. So if we know what we're looking at, we have the same equation. I should have infinite solutions. On the graph, when I start at +2 and I use my slope of -1/2 going down 1, right 2, down 1, right 2, or up 1, back 2, I should see, if I had like multiple choice or something, I would see either just one line on the graph, or I might see one line with double arrows showing that it's graphed on top of itself. But when it's the same equation, same line, that is infinite solutions. That means that they're intersecting at all points ever. Okay, our very last example. Again, neither one of them are technically in slope-intercept form. The second one I can't do much with because it's a special case line. But we'll rearrange the top one to get y by itself. First I need to move the x. So I'm going to minus x from both sides because it was positive. And I've got 3y equals -15 minus x. When I try to get rid of the 3 in front, I'm going to divide everything by 3. So y equals a -15 divided by +3 is -5. There's an understood 1 here in front of this -x. So 1/3 will give me a decimal, so I'm going to leave it -1/3 x. If I rearrange it, y equals -1/3 x minus 5. The other one is a special case line. I can't really rearrange it. It's just y equals -7. And we remember those are horizontal lines. So y equals numbers are just horizontal. If I had x equals a number, it would be vertical. So I'm going to just try and graph these two equations now. If I graph my rearranged first equation, I'm going to start at -5. So 1, 2, 3, 4, 5. Put a dot. Slope's -1/3, so I can go down 1, right 3, or up 1, back 3. So down 1, right 3, keep doing it to make it accurate, or up 1, back 3. Okay, so there's my first line. When I graph the special case line, I need to go to that value on y, so I'm going to -7, so -7, put a dot, and it is a horizontal line. So the point of intersection here is right here. Starting from the origin to read the ordered pair, I go over 1, 2, 3, 4, 5, 6 on x, so +6 for x, and then I go down 1, 2, 3, 4, 5, 6, 7 on y, so -7 for y. Alright, so some things that we didn't cover. We didn't cover no solution graphs. We know that no solution happens if I were to graph and I got a set of parallel lines because my slopes were the same but my y-intercepts were different. That would have told us that it was no solutions. Some other special case things that we talked about were vertical versus horizontal lines. I know that for my classes I talked to them about this little acronym, HOY-BUCKS, and what it stands for is it basically is a way, I'll write it this way, HOYBUX. It's a way to remember the difference between horizontal and vertical lines. So I got horizontal lines have 0 slope and they come from y equals a number. So for example, just like y equals 5. That's going to be horizontal, it's going to have 0 slope. The VUX part tells me that vertical lines have undefined slope and they come from x equals a number lines. So for example, x equals -2 would be a vertical line, while y equals 5 would be a horizontal line. It's commonly misunderstood and made backwards because we're thinking of the axis, but this is just one way if you're getting them backwards, HOY-BUCKS, to try and remember what is what. Okay, so that is the lesson on remembering how to graph. We graphed from slope-intercept, we graphed when it wasn't in slope-intercept, we graphed special case lines, we graphed one infinite and talked about no solutions, so hopefully that will help you to review.